Hello and welcome back to the course on blockchain. And today we've got a tutorial on consensus protocols. Alright, so here's our map. We've just ticked off mining and finally we are at consensus protocols, the last step in our saga. Alright, so let's have a look at what we're talking about. We're going to discuss, in terms of consensus protocols, we're going to look at first the challenges that they're designed to solve, because we've already gotten familiar with the concept of consensus protocols when we were talking about the Byzantine fault tolerance, and we understand what the whole notion is how the distributed network agrees on things. And in our case, it's how does it agree on how to keep growing, how to keep adding blocks, in which direction, how to know when to add a block and which block to add across the whole network. And so the challenge is that a consensus protocol, like as you recall in the Byzantine fault tolerance example, the challenge for the generals was to understand which command to listen to, like whether to attack or retreat. So they had to come up with a consensus protocol to solve that challenge. In our case, the consensus protocol for a blockchain has to solve two main challenges. Number one is protect the network from attackers. And we already talked about the situation where an attacker tries to attack somewhere in the middle of the chain. So if an attacker tries to change this block, then that's going to be almost impossible for them, because they would have to change all these blocks and then all these blocks on every single node. So that's not the problem we're talking about here. The problem we're talking about here is what happens if an attacker tries to put a block at the end of the chain, tries to add a new block that is malicious. And the second challenge that a consensus protocol should solve in a blockchain is the challenge of competing chains. So in a large blockchain, because it is distributed across the world, there can be a lag between nodes, especially nodes that are far away from each other. And it could so happen that two nodes that are far away from each other could successfully mine a block at the same time, like that. And there's nothing malicious about this. There's no attackers. It's just so happens because once, let's say, this one mines the block, before the information about that gets to this one, maybe it takes like 2 seconds to get here, but during the first second, this node already also mined a block. And from the perspective of each one of these nodes, they have done nothing wrong. They are in total agreement with how mining works. And nevertheless, for the blockchain, this is a problem, because it needs to be in consensus on how to keep growing. It needs to know, do we keep growing with the orange block or do we keep growing with the purple block? Because as we'll discuss further down the course, these blocks could actually have different transactions inside them. It cannot just accept both blocks and split the fee between the two. No, it has to pick one of the two blocks. And so that's the challenge. How does the network come to a consensus on how to keep growing? Because if it doesn't come to a consensus, if the consensus protocol is not in place, what will happen is you'll have this chain, they'll be conflicting, and then they'll split up into two, and then later on the blockchain will split up into 4 and 8 and so on, and then eventually you just have a ton of blockchains which are completely separate. So we don't want that. We want an integral blockchain. So that's the second challenge. And in terms of consensus protocols, it's important to note at this point that there are multiple different types of consensus protocols. And at the end of this tutorial, I'll recommend an article which highlights a couple of them, which can be useful. But the two most famous ones are proof of work, POW, or proof of stake, POS. And the one we're going to be talking about is proof of work, because that's the original one described by Satoshi Nakamoto in his paper. And also it's the one that Bitcoin currently uses, and it's also the one that Ethereum still uses, even though they're planning on moving to proof of stake. So that's the one we're going to be talking about. So where does this term proof of work come from? Well, the great news is that by talking about the information or the things that we talked about in the previous tutorials, such as mining, such as hashing, and P2P networks and the Immutable Ledger, we've already laid a very good foundation for seeing how everything comes together to create this consensus of proof of work. And so we're going to start with mining. So here you can see that where we finished off with the whole mining situation, that the main takeaway from here was that miners need to come up with this nonce, with this golden nonce, which will create a hash which is under the target, and then they will be allowed to create a block. So that's the cryptographic challenge that they're solving, and they have to go through lots and lots of iterations to get to that nonce. Hundreds of thousands, millions, billions of iterations they need to go through until they find that nonce. And so what does that mean? That means a lot of time. That means a lot of hardware investments, like into their mining rigs or mining computers, and also a lot of electricity. They have to pay huge electricity bills. Some miners, like eight to plus, like one I heard was like $8,000 per day, just in electricity, just to mine this stuff. And yeah, so as we can conclude, that's a lot of work on the side of the miner. And this hash that they have in the end, the solution to the cryptographic puzzle, is the proof of work, is the proof that they've put in all this work in order to solve the cryptographic challenge. So that's where the term comes from. That's number one. And number two is that we can see, it's important to see that they do have to put in a lot of work, because this will be important in the next slide. So now going back to our distributed network. What happens when a miner adds a new block? There it comes, there's the new block. The network or the blockchain will reward the miner for mining that block. So in Bitcoin, it's 12.5 Bitcoins. In Ethereum, it's a certain amount of Ether for adding that block. And also, the miner will get the fees associated with the transactions that are included in that block. So there's monetary incentive, there's financial incentive for miners to mine. And also there's financial incentive for miners to play fair. Why is that? Because they've put in a lot of work. So if they put in a lot of work and then they add a block that is rejected, or like they add a block that is, they found that they solved the cryptographic puzzle and they found the correct hash, and they add that block, but they've included malicious transactions, or they've done something malicious, they just won't get that reward and they won't get the fees. And therefore, they're not going to be able to pay for their electricity bill. So basically, they'll get penalized, and they don't want to risk that. So they have to play fair. And how will the network know if they're adding a malicious block? Well, it's actually very simple. Every single node before that block gets added like that, before that block is propagated through the network, every single node will conduct a series of checks. And this series of checks is very rigorous. So this is just a screenshot of some of the checks. The list just keeps going. I think it's a couple of pages long. And they check the miracle hash. They check the previous block matches the previous hash field in the main block. They check the timestamps. They check transaction list must not be empty. They check lots and lots of things. So as you can see here, it's very, very detailed. And if a check doesn't go through, then they reject the block. And so basically, at the end of the day, the network will not allow, the blockchain will not allow malicious blocks to be added to the chain. And that's why there's a financial incentive to play according to the rules. So that's how we solve challenge number one. So that's that part of the consensus protocol, that block. So once a block comes to you, you need to do all the checks, and then you can only accept or reject it. And so if the network starts rejecting the block, like if all these nodes start rejecting the block, then that's just basically the blockchain will reject it, and that block will be invalid, that miner will be penalized. So that's the first part. Now let's talk about the second part. This one's going to be more interesting. Before we move on, one thing I almost forgot. I was thinking, like, there's something I wanted to say. This cryptographic puzzles, hard to solve, easy to verify. So it's important to understand that there's a difference between mining and then verifying things. Because in mining, you have to do a lot of iterations. You have to solve that cryptographic puzzle. You have to go through all these different variations of the nonce and check the hash, and like just it's about brute forcing your way through the nonce to get the right hash. Whereas with verifying, you just need to check that it matches up. So let's just go back here for a second. So here you'll see that to get to this nonce, you just have to go through all of these, iterations, billions of iterations. But to check, to verify, it's extremely trivial. You just take all this information, you put it into the hashing algorithm, and you get the hash, and you just check that indeed it's under the target. That's it, or it is what the miner is saying it is. So that's the kind of like paradox or irony, I'd say, in the cryptographic puzzles, that you're putting in all this work to find this nonce, and then for somebody to verify it, they don't have to do any of that work at all. They just like take this and then bam, they put it into the hash algorithm, and then a second later they got the hash, which you were looking for minutes, for a long time, for billions of iterations, and they just take one iteration to verify it. And so all these verifications, even though there's a huge list of them, it takes a couple of seconds maximum to conduct these verifications for each node. So it's not a computationally heavy exercise for them. They don't spend a lot of electricity or anything like that. It's just a routine process that they do. Okay, so we're clear with that. That was us talking about prevention of attacks.